We're making a recording, but that doesn't mean you can't ask questions like normally. They are informal. Huh? I want to keep them like that way too. Huh? So. Okay, so this is our, I believe, our third lecture in the series where we're combining these three topics. And let's quickly go through what we've done. This slide I don't want to go through anymore. Just a short discussion what's different about the analytical mechanics versus the Newtonian type that we also use for multiports. It's the same stuff. Okay? And how is it different? Well, this kind of picture is exactly what's going on. All right? And actually, to be precise, this is not exactly what's going on. This is about half of what's going on. So there is a, this thing is divided in several pieces, and all we're doing here is looking at the goods themselves. And these goods could be money, it could be services, could be anything like that, and how they are changing hands. All right? This is, for us engineers, is the same as position, how the position is changing. If you have a robot arm, you know, how are these angles changing? You see? We're not talking about forces or incentives yet. We're not talking about prices yet. We're not talking about any of this. All right? Huh? And there seems to be a lot of confusion about this. So maybe just write it down. What we're doing here is what we would call kinematics. So that just involves position and velocity. All right? Now this is going to take us, at the end of this lecture, I want to finish the whole kinematics. So we're attacking these positions, which are these stock quantities, and we're attacking these velocities and how they may look, and in particular what a freestyle cruising is, all right, which are the quantities demanded or the flow quantities or things like that. All right? Huh? But kinematics is only half of the story. And really up to Newton, it was the whole story with some weird stuff thrown in. All right? Huh? So kinematics is about the what of the motion, and what you do later, the causes are in what's called kinetics. Okay? And the kinetics is about the momenta and the forces. All right? Huh? So for us, the kinetics is going to be the prices and the incentives. That's what we're going to do after this lecture. Together, they make up what we call dynamics. Now, this is just the way we, as a mechanical engineer, define dynamics. If you read an economics text, or if you talk to regular people, they may just say, because things are moving here, right, that's also dynamics. Okay? But for us, that's really not. Okay? It has to have a cause, the kinetics with it, for it to be truly dynamic. Okay? Now, I can tell you already that most economists, they just have what we would call a kinematic model. So they'll tell you what's going on or what the quantities demanded are, and that's it, right? And they may have very complicated models to tell you what this is doing, but then those things, they don't have a cause and effect. So econometric models don't have that. DSGE models don't really have that, you know? They do talk about incentives and prices, but more in an informal way. They haven't defined what they mean by a price. It just comes out of thin air, all right? More or less like Newtonian mechanics. And they certainly haven't defined an incentive or a want or a desire, right, in terms of price. Okay, so these are all steps we're going to have to take. And this is what makes us so different from them. So it's important to keep that in mind while you're going through this last lecture, all right? Nobody's doing anything yet, okay? And in your work, also make this distinction, okay? This is how you build it up, okay? So what is the kinematics of this? Well, here I have this picture of the train. All we're doing is seeing how these bananas are moving to this agent, how these are getting books and this turkey, and then whatever is moving there. You know, this chainsaw here, oh no, it's a carpet, right? Huh? So nobody is saying what these people's values are, the incentives. They're just saying they're doing this, all right? So you count the number of agents, you count the number of goods, you multiply each other, and then you look at the stock that everybody has, and that you plot down in the stock space, okay? It's just some amorphous space, All right? And at any moment in time, there's a rate at which they're exchanging this, and that is what is in your flow space or your tangent space, okay? And the way you formalize it, you take your time axis, or here's your clock. You know you have your clock. You don't know what the heck is going on here, all right? But you do know you have a clock, and you can track how much your stock is going up and down for each person, so you know how this thing is moving, and then you can look at the tangent path of that thing, and presto, you have your quantity demanded, all right? Huh? Now this is all amorphous, so what we like to do is to plot these into what we call accounts. You know, that's what bookkeepers do, accountants do, and they'll keep the stocks in a sort of a balance sheet where you keep the balances of all the accounts, huh? All right? And the flows will be in a cash flow statement or income statement or something like that, all right? Huh? And these are usually Excel sheets. What we do is, this is like the first big innovation, I would say. Instead of using all these tables and Excel sheets, we'll just plot it as coordinates, you know? It's very efficient. And once you do that, we can later on introduce the forces, and we can look at trade as a movement in a space, you see? This is the trick, huh? For any problem, what you do is first get yourself in the right space. And once you're in the right space, then you can plot trade as movement in that space, all right? Otherwise, you're just going to have lots of Excel sheets and workbooks with references, and they're all break, and it doesn't, you know, and I don't even know how you can do mechanics for that, all right? This is the tools we have to do that. All right, so the nice thing to do this is that we kind of separate these three things. You have the statements, you know, you have time itself, and then you have these amorphous economic states. And then the mapping, this is what we call the execution. This is what you're really doing. You know, that's what a decision maker does. The reporting is just what you get from your back office, like, okay, here it is, like you did. All right? Huh? Okay? So it's a nice picture. And again, the number of dimensions, the degrees of freedom. This, you take the number of agents, the number of goods, multiplied by the number of goods and services. So in dynamics, every agent will be a particle, okay? And every count, you know, would be a direction, you know. Okay. All right? So we all know this. Now, the first thing that's important, and I kind of make I made a bigger deal out of this than I did last time. There's something called the tangent lift of a curve. This is differential geometry language. So here's what happens. We all know that a course of action, you start here, then you buy this, you buy that, you end up here. All right? Huh? So what it does really, this function, you can think of it as mapping the real numbers into this stock space, right? Huh? So it maps time into this stock space, right? So every moment in time, you get a point in the stock space. But you can do a little bit more, right? I can take at every point the derivative and not only map it in the stock space, but I can also, because I can take the derivative, map it into the tangent space, okay? At any point, right? Huh? Okay? So I can, all I'm doing here is trying to figure out what that tangent vector is and say, oh, that's an element of that flow space. So I'm going to map it into the tangent bundle. Okay? So I'm going to take this thing, and as it were, I'm going to lift it one thing up. That's why they call it a lift. And they call it a tangent lift because I lifted in the tangent space. It seems complicated, but all it's saying, if you know what path you took, you also know what velocity you had at any moment in that path. So not only can you keep track of where you are, but you can also keep track of what velocity you had, all right? You can also keep track of your acceleration, and then you're in the tangent space of the tangent space, okay? You know? And what we do as engineers, we just kind of plot these things. Oh, here's your position, here's your velocity, here's your acceleration. You know, let's plot them all in there. But they really live in different spaces because they have different units, right? One is per second, the other per second squared, okay? All right? That's the idea. Now, when you do that, you'll figure out that what's happening is that this quantity demanded is going to be the change in your stock quantity. Okay? That's just part of that definition. It seems obvious, but this is what an economist would call stock flow consistency. All right? So most of their models are just pure flow models. So, you know, when they look at demand for oil, they say it's so many barrels a day, but nobody's really keeping track where those barrels are going. You know, you have a demand line. What you really should do is, okay, they go in the stock of these things. So when they were building computer models, they figured out that if you don't do that, then your oil is just disappearing in nowhere, it's no good. So they introduced this concept of stock flow consistency. So the idea of the tangent lift formalizes that, right? Huh? Okay. All right. So it's kind of pretty what's going on, because the setup, the definition of velocity, kind of formalizes the agreement that you have to be stock flow consistent. All right? So it's a non-trivial thing, although it all feels so trivial. All right? Huh? Okay? Is that clear? It's also part of you getting used to this language, right? Huh? You're also going to have the cotangent lift and the double tangent lift. That's the acceleration, you know, now. Huh? Okay. Then we talked about these commodities and how this all would work, you know, and I guess it's kind of trivial, because you take this manifold and you just plot it on the real line, and you know, the only thing you have to see is that attaching a flow to each stock position means adding an extra dimension, all right? And you have to add that dimension at every flow point, okay? So the term that is used is the fiber for this, okay? Because they're kind of these fibers sticking out, okay? But you can't think of that this is a square angle, or, you know, that makes no sense. Huh? But you can do this, because now that point is in both fibers at the same time. That's impossible, right? Huh? All right? Huh? So as long as you don't do that, you're going to be fine. And this is our typical state space, right? So, you know, now we'll do Q and Q dot, huh? You know, and then you'll have an A matrix, and then you'll have here Q dot and Q double dot, because they're the derivatives of these. Okay? So you can already see how this whole setup makes it easy to solve differential and view the differential equations just by following vectors and stuff. All right? Huh? Okay. Now here, but the thing gets complicated very quickly. That's why this terminology is pretty good. I mean, this is in for 2 dimensions. So you're gonna get 4 dimensions in your tangent bundle, right? Huh? Of your space of economic states. Yeah, why? Because you have Q1, Q2. Those are your 2 commodities, apples and pears. And then you have the demand for apples, and then you have the demand for pears, right? Huh? So you got 4. I gotta plot that, right? Huh? So the picture of saying, well, at any point here, I have some plane of where the flows are is a good one. You know, I don't want to say there's a crossing here. You know, it's just plane hanging out there. Huh? You see? So it's a fiber of planes then, at every point. Huh? Okay? So, and then we went through this example. So this was our kind of first non-trivial manifold. So we have these 3 different accounts. We know that there is you could be a portfolio of stocks, it could be anything. You know you have a certain amount of funds. All you're doing is looking, or it could be a basket of fruits. You know, you have so many apples, so many pears, and you're just changing the mixture, right? Huh? Now, all you do is we'll move along a simplex, all right? So you're going to be on a 2-dimensional submanifold of this bigger space, all right? It's what we would call a holonomic constraint. So you can have 2 coordinates to describe this. And they have these barocentric coordinates that we would use. And those are the relative fractions, okay? So you see cool stuff. You can use affine coordinates a little bit different. So you can, the thing about this is like, you see, when you rephrase this portfolio composition problem in this way, you can say, okay, it's cute, but it's a little bit more than cute. Because, for instance, colors work this way, right? Colors are a manifold, when you mix green, red, and blue, and they live on this, same manifold, okay? And you can use the color coding also for, it's just a different coordinate system. You can use hexadecimal coding for all I care, because it's got these 3 hexadecimal points, and then you have 3 axes, okay? All right? Okay? So we're abstracting nicely away, So you can think of this as positions, you can think of this as stock quantities, but you can also think of it as colors, And this is the trick we always play as systems and control, right? So we are able to recognize some situation in somebody's domain, and then abstract away with it, make a mathematical models that has the right structure, and then start working with it, and then later we descend back into reality and make our predictions, okay? All right, so this is all fine and well. And now I want to look at we also looked at some other spaces, right? Now these are interesting ones. So this is a typical one in the theory of capital, right? You have a certain product and you have certain capital. So land, for instance, it doesn't depreciate and doesn't get worse. You don't get more of it. So it's constant, and you'll get this crop coming off, and you're on this submanifold here, right? Huh? Now, would you just use the amount of crop? No, you wouldn't. You would divide your crop by the amount of land you have, all right? Huh? So you will take this distance here, divide it by that distance, and then that's what you would do. And that's an angle, okay? So your yield or your return is an angle. So this is the big thing here. If you start looking at these kind of pictures, then you can say the coordinates are all a sort of a return, and the return is a dimensionless thing, and is what we would refer to as an angle. Now, normally when you think of an angle, you would think of a circle, right? And you take this piece of arc length here, and then divide it by this radius, right? And that works here as well. It's called the total return. So I had an example of chickens and eggs, but let's take the example of the accounts. So it was a mortgage, right? An annuity for a mortgage. So this is your principal, and then you make a payment. You make the bank has a principal. The bank receives your interest payment, and then the bank receives a repayment of the loan. And then it goes like this. They get a smaller interest payment, bigger repayment. And if you make that infinitesimally small, you'll see you go around in a circle like that. Okay? Okay, this movement has our conserved quantity is R. We'll call that the amount of capital, right? Okay, the resources, I call it. All right. What's this? And this is the total return. So this is the sum, go every little piece ds here that you're going is going to be a sum of an amount of interest you got and account of repayment, right? So if you add that all up, you're going to have the arc length, and you divide it by r, now you'll have the return in units of pi, I guess, right? Because you're dividing, okay? All right? So here, this is it, right? So we worked with Rabobank on this. They have big tables, and then graphs, how it goes over time, and things like that. They just couldn't believe you could put it in one trajectory that you just go, right? It was so simple, right? So you just make a coordinate chart. There's people who bother themselves about saying how you should graph objects. So there was somebody, I forgot his name in my day, who was making a big to-do that the best way to do it was maps. Now maps is exactly this, right? So a map, you take some manifold like the Earth, like a sphere, and you put it on a flat space, right? And you get a lot of information, right? Rather than plotting that mountains are at this latitude or something, you can, some kind of graph, right? That's what we're really doing here. So we're making maps of your annuity. This is a savings account, right? So you get your savings, and then it gets compounded in, and then you get more interest, and then you compound it in. Okay? That's the hyperbola you get. And what's conserved is your initial capital, your initial investment. And that's the hyperbolic radius. Okay? Now we're gonna do a lot with this example. I'm gonna build this out. This is an important example. Okay? And this is really, see, this is one of the problems with this setting up analytical mechanics is that you end up always proving, if you look at Landau and Lifshitz or something, they end up proving it only for like commodities, now. And then they have to have special tricks to get it done for other coordinates, by going to spherical coordinates and adjustments, And I like, and then more mathematical text, there are some good exceptions. They tend to just say, oh, we have manifold, and oh, here's one example, and then be done with it, and then go on. And what I want to do with this lecture is like finish off this whole thing. Like say, really, in economics, we always have manifolds. And it's not clear what is a constant quantity demanded, all right? Okay? All right. So, to do so, I'm going to do this. I'm going to use two theories that are somewhat advanced. And the one is the theory of Lie groups. And Lie was probably the most famous Norwegian mathematician. Is that true? Lie
and Abel, I think.
Abel, yeah.
Abel first and then Lie.
Is the most famous, huh?
Yeah, I think so.
Yeah.
We named the prize after Abel.
Yeah, I see.
But he just lived for a short while, and then Lie stayed on for a long time, and he was working in Germany most of the time too.
Yeah, that's true, yeah. With Klein, huh? Yeah. So, and the other thing I'm going to use is a theory of Riemannian geometry, all right? So Lie groups, most of you have heard of. In some courses you'll get it. They're basically transformations, okay? So basically all Lie groups are some sort of rotation, okay? Just think of it as a rotation, but can be weird ones. It can be shears, can be, hyperbolic rotations, whatever, huh? Okay? And what makes them Lie groups is that you can do them incrementally and differentially. You can do a small rotation, infinitesimally small, right? Huh? Yeah, you can do an infinitesimally small translation and these kind of things. And you can invert yourself, right? And then you can do nothing, right? These are all things we want to do, right? So if you do some kind of activity, you typically think of buying something, but you also want to be able to go back. Imagine that, going back, that's disposing of the thing. And at a minimum, you also want to be able to do nothing, right? So often you'll see these things you can set it up, and your activity can be described by this group of transformation called a Lie group. And we'll see lots of examples. We've already seen one, but we'll work through them, okay? Now, Riemannian geometry is, okay, so what are they good for? Well, they're really good at identifying the symmetry, okay? In a situation, okay? So you use for that Lie groups. Huh? That's what they're attended to, okay? So this was a famous idea, I think in the 19th century by Klein, and it was, he presented that in something that became known as the Erlangen address. It was a big speech he gave, and afterwards it became to know as the Erlanger program to go carry this out. And the idea was, what is a symmetry, okay? So if you have a square, it looks symmetrical, right? But why? What is that symmetry, right? So you can say, well, It's not so easy to describe what makes this thing symmetrical, because a rectangle is also a symmetry, right? Like the one we saw of those portfolio composition. So what's the difference between these two symmetries? Okay? And a circle is also symmetric, right? So what's the difference between that and a square? Somehow we feel the circle is more symmetric than a square, right? Huh? And would you say that a square is more symmetric than a triangle or not? Huh? That's very hard, right? Huh? The problem is you don't know what a symmetry is. You're just kind of guessing. And once in a while you got to sucker your thumb and come up with an idea. All right? Huh? And you don't really know what it is. Right? You just recognize it when you see it. Huh? Okay? But Klein, he was a very good German mathematician. He figured out what it was. He says, the symmetry is determined by the group of transformations that leaves the shape invariant. Okay? So what is invariance? Well, that you do something to it, and then afterwards you can't see the difference. Right? And a group of transformations, what are they? Like rotations or something like that, right? So what is a square? Well, what's the group? Now we can rotate this thing, right? Huh? Okay. And what transformations leaves the thing invariant? Huh? Well, that's a 90-degree turn, 180-degree turn, 270, and then 360, which is the same as doing nothing, right? So it's got 4 symmetries, say. Huh? So the symmetry, you know, huh? So 4 things you can do with it. Huh? And then you won't see any difference, right? Chop, 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 chop. Huh? Okay? What about a triangle? Well, 3, right? 1, 2, 3, whatever. Huh? Well, you can bring every vertex to another vertex. There's only 3, or you do nothing. Right? There's 2 ways, huh? Or do nothing, right? Huh? So 4 is bigger than 3. So a square is more symmetrical. Okay? What about a circle? How many ways can you rotate that thing? Very large number, right? Huh? Infinitely. Huh? So it's the ultimate symmetry, right? Okay? So hexagon has already got more, and then an infiniton is a circle, right? Huh? So this is the solution, all right? So you see, this is a clever idea, all right? Huh? So the idea is that if you have this group of transformations, so these rotations, then you can say, you can categorize what the symmetry is. So first of all, you know the symmetry is going to be some rotational symmetry because you have the rotation group, not some kind of translation symmetry, right? Huh? Okay. And you can say, you know, how many times you do that. Now what Lee did is he looked at these continuous symmetries, that you have infinite things. That means an infinitesimal transformation, right? Huh? So he looked at circles and these hyperbolae, you know, and that kind of stuff, all right? Huh? Now why are symmetries important for us? Well, in economics, you will have all kinds of things where certain things just don't matter. Like if I just take the theory of demand, they'll say that, you know, your price is determined by the quantity you supply or demanded or something like that. So they got some kind of flow here, right? So it doesn't matter where this thing is, what your stock quantity is. No, under this theory, not, right? So the whole theory is symmetric under translations, okay? Right? That's what it means, okay? So if I have here this one-dimensional manifold, I can say, well, if I have this symmetry, I can move this thing over here. It will be the same thing, right? Huh? So it's a symmetry group of translation. Now that group is called the translation group. I usually denote it like this, R and a plus, because the plus means you're adding it, right? So a translation is you add this to that, right? Huh? Okay? And then it makes sense to say a constant flow is the one that is always the same, right? And here is the same, and you can plot it here. You can make a coordinate, so an account, where you just say this is equal to that that distance you measure here, all right? And then there you go, all right? Now, in order to do this, you need one more thing. Somehow I need to be able to measure distance here, right? And remember, the space didn't have a distance measure. So I need to say how much of a stock. That it's 5, not just a bunch of points lying there. Now, that's done with a metric, okay? And you have the famous Euclidean metric, right? So you can just calculate the distance between 2 points. You put your ruler there, chuck, and there you are, right? And if you do coordinates, you take Pythagoras' thing and you sort it out. All right? Okay? So a regular type of commodity theory that always we'll be looking at, and that's the same as Newton's theory, you assume that the whole thing is invariant on the translation group. You can take your whole experimental setup, move it somewhere else, and the laws of Newton will tell you exactly the same thing. It's called also the homogeneity of space. Okay? There are other symmetry groups. They can change the inertial reference frame, and you can do that, but I'm kind of staying away from that right now. All right? Okay? All right? So that's important to see, because it's only because you know what the symmetry is that you know what a constant velocity is, or in this case, constant demand. If you didn't know that, how do you know your metric is all weird, right? Okay. Now, one way to think about why this is the case is that the way we've chosen to measure space is so that free motion appears as if it comes. We'll come to this later. All right? Okay? It has to do with the squared form of the kinetic energy that looks like, a Euclidean metric, really. Okay? But we'll come to this later. So I think there was a question from you that says, well, what is a constant velocity? What's a constant flow? Well, that all depends what your symmetry group is on this thing, right? And then you have a metric, and what you do is you look at which the group that leaves this metric invariant. It's also called an isometry, right? So you can move it over and nothing changes with the metric. If you do something that is all different, then you didn't have a symmetry, all right? This is the setup. This is we're going to generalize, all right? Okay, and here's the first step. So in economics, rarely do they do this. Okay, rarely. I mean, maybe some inventory or commodities, but they never look at that. They always look at economic growth, exponential growth, as the de facto equilibrium movement, right? Okay. Now, what the heck would be the symmetry group then? Okay, and what is the invariant metric? So they must have done, they still have the same line, right? This is a population, this is growing, or a count, this is growing exponentially, or whatever. Your economy is growing, that's what you have an economy growing. But what the heck happened? How all of a sudden is this exponential, and here it was this linear, right? Okay. And what happened is you're using another group, all right, and you have another metric that is left invariant. So if I look at stock returns, it's really clear. They're always plotted on log paper, right? Nobody plots the S&P 500 like that, because you see it's exponential, you immediately go to log paper, right? So what does that mean, right? What it means about return, why is that? Because these returns, they multiply, right? If you make 5% and then 5%, you got to keep multiplying by 1.05 all the time, right? So instead of adding, you're multiplying, all right? Okay. And the way you measure distance is by looking at a displacement and then dividing it by the amount you have. So you look at a proportional fraction, right? Or a percentage change. And that's the way you measure distance. So not the real change, but the percentage change. This is sometimes called a hyperbolic metric. It's a little confusing because it doesn't necessarily have anything to do with the hyperbola. It's just the count of differential equations. Huh? This is what Klein called it. Huh? I call this an elliptical metric in higher dimension spaces. All right? Huh? Oh no, parabolic metric. Sorry. Huh? So this is forget about the terminology. You see? Now, if I now go through the whole business, then this, if I do that, then the distance here is not Vt, huh? Just the flow times the time, but it's e to the Vt, all right? That's what that distance is going to be, okay? And the way I get back the scaling is I take the log of that, and then I'll just recover my regular, and then it will look as if it's linear. So the multiplication will turn into an addition, huh? And this whole thing will turn into a nice linear thing, but only in these funky coordinates, okay? All right? So here you have two spaces that look the same, but as soon as you put in another metric on it, another way of measuring distance, right, which is another way of measuring your stock, you'll get a completely different flow, all right? Okay? Now this you do all the time. You just never thought about it. And this is, economists do this all the time too. They'll say, oh, okay, let's take log coordinates. We do that, you make a Bode plot, you log coordinates. And then, oh, no, a straight line in my Bode plot, you know? Huh? Yeah, well, but you're using a different metric for frequency, right? And for amplification. Why? Because you're measuring it in decibels. And a bell is a logarithmic metric. And why are you doing it? Because that's the way the ear works, right? The ear, twice as loud, it has to be the exponent. So the ear takes the logarithm, okay? That's the way the ear works. All right? So for you, twice as loud is actually a multiplication, is a power, all right? Okay? If you measure it in watts. You know this, right? Huh? And for the economist, economic growth, it's the same as your ear, okay? Huh? Okay. That's why they take it, because it's very human to do this, all right? Huh? Our eye works the same way too, all right? Okay? We'll see this later, all right? So a lot of our human senses, they work in a logarithmic way. This is how we feel it, okay? Huh? Well, the eye, only the frequency part. Normally, when you use your eye to measure distance, it's not logarithmic. You can actually see the, okay? All right, huh? So a lot of intensities are measured on a log scale. So this is a very natural thing to do, okay? So you see, don't be too quick in saying, oh, I know what a manifold is, a straight line. I'll just use the addition group and start moving this thing around. No, because if you move this around, it's going to get bigger and bigger and bigger, right? Huh? Okay, and when you move it back, it's going to get smaller and smaller. Huh? All right? Huh? In your, huh? So the way to, you know, this is one dimension, but this business, you know, normally you just throw in your log scale and you go, blah, 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 blah. And what is this equivalent to? Well, really, it's, if you look at the Earth, it's a globe, right? It's a sphere. But you make a map where it's a flat. But you've got to put a legend on that map that tells you how you're scaling things up and down compared to the assumed metric, which is this one, right? Huh? You're thinking that you can measure distance with a ruler, but you can't, because you got to work your way back through that, huh? Whatever the projection is, like the Mercator projection or whatever. All right? Huh? Except maps are in 2D, and this is a 1D map, so it feels a little funny, but this is what it is. All right? Huh? Is that clear? Huh? You're looking a little bit puzzled, huh?
The axis on the left, the bolded black axis, is that the stock space?
Yeah, this is the stock space.
Okay,
right? Huh? So I make the Stokes spaces always black.
Yeah.
So in this case, it's one-dimensional space. I just draw it as a line. I could have done this,
Yeah.
right? And then this is the tangent space at this point, right? Huh? But I drew it as a tangent space, right? Huh? Okay. And here, I forgot to draw. I could have drawn it, you know. I just, yeah, you spend a lot of time with this, huh? With these ticks, you know, really, you know, huh? And then if you're going at constant speed, that's this, you'll have some constant speed. I know it will be a constant expansion factor, right? I mean, how do you want to, what's the symbol for an expansion factor? I don't know. Gamma or something, right? Huh? I don't care. Huh? You know, huh? That's an expansion, right? Or a growth factor. So constant growth would look like this, huh? In this thing. But if you do the other one, here now, huh? Goes up, huh? Okay?
So if you take the translation group and you put a Euclidean metric on it, then you get a result on the right. It's like kind of a chart almost.
Yeah.
And it behaves in a very nice linear way.
Yeah.
If you take the multiplicative group, which is a different beast, which you apply a hyperbolic metric,
Yeah.
then you again get something that acts the same way as that linear space.
Yeah.
to the right.
Yeah. Yeah. If you take the right to chart.
Yeah.
Yeah, which is, here it's the identity transform. This is supposed to be the identity, right? Huh? And here you have to use a log. If you do the Mercator projection, you have to do some complicated, I don't know, this divided by some other thing, right? The radius. Huh?
So the question then is, do these metrics exist for more than these relatively simple groups, like metrics that...
Sure, any group you can, I mean, I kind of exhausted the two groups that you have in the real numbers. You have addition and multiplication, and they're related through the log, right? Huh? But you can other, you know, what is in the guy across, you know, he does max min. So he's got the max metric, you know, it's another metric. You know, you can, square metric or something. I don't know, you have weird metrics. You can do anything you like, huh? Okay? And then you look at the group that belongs to it. If it's, you got to set things up nicely. So you have the metric, and then you have the group that leaves it invariant. So what you want to do is you're here, and you're, you know, you have your metric built in, and you're here. And what I want to do is, when I move over there, that I'm not going to think, hey, my space is all messed up, you know? Huh? I want to have a metric that, you know, and because if it gets smaller, I feel I'm slowing down, right? Huh? And if it stays the same, then I feel I'm going at constant speed, you see? So the metric, if you know the metric, you can also define what translation group gives you the constant speed, all right? Now, this one will give you an exponential function. This is the origin of the exponential function. Now, what's kind of cool is that this thing can also be seen as an exponential function, okay? And it is called the exponential function, right? Huh? It's just a special one because it's really the identity. And if you looked at the exponential function, you know, the Taylor series is 1 plus x, you know, huh? And all terms become 0 except this one. That's all, right? Huh? We'll find some other ones later, right? Huh? So the big thing, I mean, here it looks silly because why not just keep track of it separately? But the big thing you're going to see is everything is a special kind of exponential map, okay? Now, you can say, it's cute, but for economics-wise, it's useful because the exponential growth is just the basis. And you have all these other very complicated motions, and it's good to see that everything is this exponential, but then in its own way, right? Huh? So you can do any weird thing in any weird dimension. As long as you have a group and an invariant metric, you'll be able to use this machinery, all right, of the exponential map, all right? Okay? We'll move on to the next example because that will really drive it home because that will also be something that you're familiar with. And all of a sudden you'll realize, oh my God, this is working. And then I want to go further and further. I want to convince you that this is the way to do kinematics. This is the thing that just brings it all together. Otherwise, I have 5 of 20 or as many options as you want. You know now? Huh? Okay? Okay? So let's look at this thing. So you remember this. This is our amortized loan. This is our, just yielding, crop yield. And this is our own compounding, right? Huh? Thing, growth. Huh? Or compound. Huh? Okay, this is the regular growth. Now this is, I like this. Okay, so what happens here? Let's look at this amortizing thing, right? So I said this before. So here's the exponential function. This is what it does. I actually don't know what this is yet. I'm going to have to plug in something, some movement in here, right? Huh? So let's look at this exponential, this amortizing loan. What happens, okay? So here's what happens, as I said before. You first, let's think of this as the complex plane, okay? So this is the real axis, and this is the imaginary axis. And I'm first going to focus on this imaginary axis, the real imaginary axis. So I'll have this thing of I squared equal to -1, right? Huh? Okay. Now why is that correct for a description for an amortizing loan? Or one of these chickens that are dying after they get an egg, right? Well, here's what happens. So the first thing you do, just follow what happens here. What's the first thing you do? Well, first you get your chickens lined up, right? Or you get your loan, huh? Your mortgage. So that's 1. Sure, I moved 1 on the real axis. I just took a loan of 1, okay? Right? Then I'm going to have to pay interest, right? So that's this. I have to add a term in the I direction, right? Huh? Okay? So let's add that term. So let's say the rate is, so we're going at this speed, huh? Okay? Let's keep it 1. Huh? I don't know. It's just the simplicity of it, right? Okay. Then what do I do later? Okay. Then I'm going to go in the -1 direction, right? Huh? Okay. And then I go to the -I direction, and I go like this. Well, let's make it a little bigger. Huh? Huh? Okay. This is what really happens. Huh? Okay. Huh? So that's exactly what happens here, okay? So suppose I take this thing here is my angular velocity, right? So that's the same as this velocity here since I'm dividing by 1, okay? Huh? So I have this 1, then I do here, I get plus I omega, right? Huh? Then I get plus I squared, and I do omega t, huh? Squared, whatever, and that will be a -1, huh? So I work my way around, and I exactly get this thing. Well, you know this anyway, right? Huh? You know this result. So I collect all my real terms, I collect all my imaginary terms, and I define cosine to be all this. By accident, this is how I define it. Huh? All these real numbers. I define these to be all the imaginary numbers, and I'm done. You see? Huh? Okay? Now, you have to admit, this is also an exponential function. But it's an exponential of something weird. It's an exponential of an imaginary number, right? Now, the guy who invented exponentials, a long time ago, he didn't know what to do, what an exponential of an imaginary number is, and neither did you before somebody told you what it was, right? This is Euler who first figured it out, and it was all magic because, huh? Okay, huh? This is what you get, okay? But really all we're doing is going through this Taylor series, and what's this Taylor series? The Taylor series is nothing but 1 plus x over n to the nth, and then we take the limit, which is just regular compounding, discrete compounding, but then, now doing it infinitely finely. It's just that when you're in a line here, your increment goes in the same direction, the real direction. Here, your increment goes in the orthogonal direction, right? The I direction, okay? So that's why I is 90 degrees. And then if you do, the next step is going backwards. So you make another 90 degrees, right? So I squared is minus, is 180, because you went backwards. I to the third, you're going to go down again, okay? This is how you add them all up, okay? So that's all that's happening. There's nothing too exciting, And this is just a bunch of definitions. I mean, you just define this to be that, and there you're done. Nothing magic, okay? So we can think of an amortizing loan, an annuity, also as a compounding thing, exponential growth, but with imaginary exponents, okay? So what's really happening is, what we're doing here is we're taking this tangent line here, and we're just wrapping it around the circle, right? That's why you get the I, okay? That's all counting. So it's the same. The rotation is also an exponential, okay? That's weird, okay? Now, let's jump to this growth thing here. Now, this growth thing is a little bit different than the growth we had before. The growth we had before, we just had one thing, and it was growing totally by itself. You know now? I always find that hard to imagine, how something can just grow by itself. I prefer to see it as follows, that I have some kind of, population, right? And then nobody dies, or at any rate, less people die than are being born, right? And then in step one, a bunch of babies are born, but they are in a different dimension. They're in the imaginary dimension. Now, I'm going to call that the J dimension, right? Okay? And then these babies grow up and they add into the population. Now the population is bigger. The next step, next generation, you get more people, and they all get added in, right? And then you can get this kind of hyperbola going. All right? You see that? So this is another complex number, but now this J squared, like J is not 1, but J squared is 1. Because when you first do a J and then another J, right? You end up going a step forward, all right? Okay? And if you work your way through the same exponential function, you'll have this number will turn out to be that, and you'll get the hyperbolic cosine and hyperbolic sine. And why? Because all these minus signs that you had here now have plus signs, and if you look up the definition of the hyperbolic sine and cosine, you'll see that that's just it, okay? So what do you see? This point here is there's the cosh, and this here is the sinh. So what you know is you see that if you have a growing population, you know that the amount of babies born is the sinh of that angle, right? The total return is the angle, and the amount of adults, that are of age is just going to cosine hyperbolic, all right? And the whole thing is exponential growth, but in the complex plane, okay? So you get the right thing. Just like here, we know that after, a total return of this is going to be the cosine for the bank. So that's the principal that's left, that's not paid off yet. And the sine here on the imaginary axis gives the total interest received by the bank, okay? All right? This is all correct, okay? See, this exponential function is just a killer. Now you also know what it means to have a constant velocity, right? Because that's when this rate of return, Q dot, is a constant, This is this omega, and that's just when you have an angular velocity of omega. But that one is different for this one than for that one. This one is turning in the usual velocity, but yet we call that constant, right? Of course we do, right? So suppose you're on Earth right here, And here you start off here. I don't know where that is, right? Huh? Now, what is a constant velocity? Is it really that you end up here, that you're going up in the sky in the North Pole? Of course not. Now, you're just going like this. Huh? That's what you would call a constant velocity, right? Otherwise, you're taking off. Huh? Okay? The same with this hyperbola. So constant growth rate is going to be that tangent vector that is the derivative of the exponential map. All right? Huh? Okay? So the exponential map gives you the constant growth factors. All right? Now here you say, wait a minute. This is just, here really it's true. This thing is just going straight up. Isn't this just the addition group? Well, yes it is, but no it isn't. See, what I would do here is I say, well, I'm going to also call this the epsilon axis here. And epsilon squared is not -1, epsilon squared is not +1, and what's the only other option? Epsilon squared is 0, right? Okay? So what does that mean? I says, I use this land, I get some crop, right? Huh? And then what happens? Do I get more land? No. Do I get less land? No. I just get nothing more after I make another move. Nothing happens, right? So epsilon squared is 0. Okay? The land doesn't grow. The land doesn't amortize. Huh? So first I get the crop, then nothing happens. And then I get more crop, and then nothing happens, right? Okay? So what happens if I look at the Taylor series? I get the 1 here, I'll get some epsilon here, this one I'll get an epsilon squared, all these terms will fall off, right? Huh? And what do I get left with? You know, now here I get an epsilon omega t, and I just have linear growth starting at 1. You know, which was exactly this point. Okay? And here is the exponential map. All it says, the exponential map of this is 1 plus epsilon omega t, right? So you can think of this as a sort of special cosine epsilon, and this is sort of a sine epsilon, right? Huh? Weird cosine and a weird sine. Or you think of this as the very small omega t approximation for the cosine or the cosine hyperbolic, one of the two, right? Huh? So the first, this is what we usually do. That's why I call it epsilon, right? Huh? So when we look, what we say linearizing, what we really mean is that this is 0, right? This is the second order terms and higher are all 0, all right? Huh? And then the exponential map will just give you the right thing. It will just give you linear growth. Yeah, see? Now, what are the metrics on here? Well, we all know what they are. You have this metric on this ambient space. If you take that Euclidean metric, then you can figure out what the induced metric is on here, and then you also know what the, that's arc length, okay? And then you know what it is. So arc length is divided by your resources, your capital. That's what I would call as total return, right? Huh? So that's the angle. The angle gives you the normalized arc length. Right? Huh? That's what I would call the return. So the arc length is the physical return, and the other one is the percentage return. Right? Okay?
Suppose we have a combination of these three. So I know you have the group of quaternions as a group, and instead of an epsilon you get a k.
All right. This one you mean, huh?
Yeah.
All right. So, yeah, let's just do it. Huh?
Yeah.
Okay. I was going to do this other one here, which is SE2, right? Huh? I don't know, which one do you want to do first? Huh?
What do you want?
Huh?
Interesting.
Huh?
Yeah.
Both are interesting. Huh? Yeah, since you asked the question, let's do this first, and then we'll go back to, huh? Because there's a couple of things that can happen. Like, what about this point? What about if that moves, right? Huh? Well, what happens then? You know, it's more complicated, right? Huh? What if you have another thing here, right? That's my next slide. So we'll skip that, huh? And then come back to it. I still have time. Okay? That will be a corporation or a business. All right? Huh? Okay? This is just a single account. Okay? And then Jesse wants to know what happens if you have more of it. Now, this was my last slide, and it just got complicated visually, right? So you'll have to bear with me a little bit. I just didn't have enough time to really make this thing cool, right? So here I have one with, three amortizing possibilities to amortize, okay? And here I have something with one kind of amortizing thing or reorientation, right? And two growth things, all right? So let's start with this guy, okay? Now, I've drawn this as a sphere here with a plane through it, okay? And I've written these quaternions. Now, this is not totally simple, but it's, if you first, let me first go through the mechanics, because you all know that, and then we'll translate it to economics, right? So if I have a plane, like here, how many dimensions does it have? It has 2. And how many possible rotations can you do? 1. So the circle, the rotations, you can only, because for rotations you need a plane, right? And there's only one plane in the plane, right? For translations you need a line, and there are 2 lines in the space, right? Okay. So this is a one-dimensional manifold, okay? Right? That's just the angle. Now, if you don't pay attention, you would think that if I have 3 dimensions, that I have a 2-dimensional manifold. But that's not true. Because how many ways are there to rotate an object in 3 space? Well, there are as many ways as you can find orthogonal planes, because every rotation happens in a plane, right? And the 3 rotations are 3 planes. And how many planes are there in 3 space? Well, there are 3 planes, right? The xy plane, this plane, and that plane, right? Okay? You can also do 3 choose 2 or something, right? And you'll figure it out. That's how many planes you have in 4 space, okay? Now, what we normally do is we say, well, you choose 3 axes here, right? But I hate this. This is not good, because in 4 space it breaks down, and in 2 space it also breaks down because there's no axis. There's a point somewhere, okay? So it's better to think of planes, okay? So when you do a rotation in 3 dimensions, you first choose the plane in which you're rotating, and then you choose the amount that you've rotated that plane, okay? That's what you do, all right? How many parameters do you need for the plane, to choose a plane? You need 2 angles, right? You tilt it one way and then the other. Azimuth and pitch, or pitch and you're from aeronautics, pitch and roll, I don't know, you yaw, and then you pitch or something, right? I don't know, yaw and pitch, right? Then you have the, and the roll, how fast you rotate around it, right? Yeah. Okay? So 2 to find the plane in which you're rotating, and 1 the amount of the rotation in that plane, right? Okay? Right? So it's always confusing why 2 dimensions have 1 rotation but 2 translations, and 3 dimensions happen to have 3 translations, and 3 rotations, 4 dimensions have 4 translations, but way more, rotations, right? Because you could, how many ways are there to choose a plane in 4-dimensional space? Well, it's 4 choose 2. I don't know what it is, 6 or something, some huge number, and it gets really big, right? Okay? And then an axis is a plane, right? So that's why axes are not so great, okay? All right. Now, so there, how do you describe this thing? So one way to describe it is say, well, here's this plane. I'll just draw an orthogonal vector, right, in this case. And then so that has two angles. And then I'll give the amount that you're rotating around that. So I'll choose an instantaneous axis of rotation and then the amount of the rotation, right? Those, I believe that's Euler angles, right? Huh? Okay? Right? That's one way to describe it. So that's what was the meaning by this sphere I drew here. So I drew the plane. That plane should have gone through 0, right? Huh? And then I forgot to draw the, in this plane should be another rotation, all right? Okay, so that's a group of transformation, because whatever you can rotate back, or you cannot rotate at all. And that group has a name, and it's called SO3. Okay, special orthogonal group in 3 dimensions. SO2 was in 2 dimensions, okay? All right, huh? Okay. And one way to describe this is through a system called quaternions, okay? So now what you do is you label all these axes, you call these all imaginary axes. There's also a real axis, but you can't plot it, right? Huh? Okay. And then you look at rotations around these axes, okay? Huh? And then you take the exponent. And then you get a rotation. It's called a versor, and this is called a vector, okay? Huh? And these axes are all like I squared, j squared, k squared, all -1. So if you do a rotation, you'll get -1 around the axis, okay? All right? Huh? So it's a little bit different than the regular complex plane, where the imaginary axis was the tangent. Here it's the orthogonal to that. It's just a little bit different. And that's why you get a factor half and all kinds of things. All right? Huh? So that is what's going on, right? Now, how can you give this some economic meaning? This is a complicated group, right? Huh? Okay. This is a complicated group. So, very hard to imagine, but it is a group. So it's very hard to imagine, to picture it, and this, and such. People break their head over these quaternions, at least Hamilton did. People break their head over all of this. Now, why is this so complicated in economics? Suppose you indeed have 3 things, right? Like you have chicken. Of course, they give these eggs, right? Huh? But you can also sell these eggs for money, right? Or credit, say, huh? All right, or you can choose the chicken for money, or you can choose it. So you can choose this to be your business, it's the plane, the egg, money plane, you buy eggs, you sell eggs, I don't know, huh? Okay, huh? And you get another cycle here that's called the credit cycle instead of the crop cycle, okay? Huh? You can also choose our old one, you can choose this plane, huh? Right, then you can choose this plane where you sell your chickens for money, right? Huh? So you can do anything you like. There's all these different businesses there, as long as it all amortizes. All right? I just assumed that. Okay? And you can take anything in between, and then you can go at any rate. Now, this is a complicated business. You see, that makes running a business difficult, because you can first try to go in the chicken business, halfway go in the egg business, and then you go to money business, and you turn things around, and you end up somewhere else. Nobody says this is commutative, right? Which we know it isn't, because if you do rotations one after the other, you're going to end up somewhere else. So if you first are in the money business, and then in the chicken business, and then in the egg business, huh? There's no, if you change the order, you're going to get a very different result, okay? Huh? So this is a complicated problem, huh? Just the kinematics of this. We're just talking kinematics, right? Huh? So, but it is completely equivalent to the problem of rigid body rotation, right? Huh? Okay. And that is solved. I mean, you spent half a course on this, I believe, huh? Just to deal with these matrices and everything, huh? And then you really don't deal with the exponential map. You could, because if you have some angular velocity matrix, you can write it as a matrix, right? And take the exponential map of that, the matrix exponential. But cooler is to use these quaternions. So they'll do this for you. So it's another way to use this exponential function, okay? So you look at infinitesimal motions around at some point, and then you take the exponential function, and it will tell you what path you take in that Lie group, okay? In that configuration space. So a business in 3, other than something with just two things, can be quite complicated. Huh? Of course, economists don't assume that. They don't have all this amortizing loans going every which way. So they wouldn't be able to solve this. Well, in reality it may happen, but you'll make some approximation. I don't know how you do it. Huh? Okay? Now here you can do the same thing. I just show some other dimensions. So I have these growing things, a deposit account, so some investment, some savings, and I throw all the interest I get on the same account. Huh? And then you can think of this as, what mix I do of these two, right? Huh? Okay, huh? And then, okay. A little bit made up examples, because you see, normally these things will be all stretched and, ellipses and complicated things, and I just want to keep it simple, because they're really the same group. You just have to rescale a bit, all right? Huh? So what's cool about these ones is you get that non-commutativity, right? So in SO2, when you're just doing this, you can be like, you pair of your law, but you can go backwards and get load some more, and it makes no difference how the order in which you do that, right? So if I'm in this thing, I can go over here and I can like recycle and do a clawback, and it makes no difference. I can do this, no matter what. Doesn't matter how I got there. But when I'm in these kind of spaces, my business is going to get more complicated. I have to make decisions. I can't just say, It's like the driving example, right? If you're steering and driving, that's actually going to be in the other one. You can't go and instead in a parking space do all the steering and then afterwards do all the driving. It's not going to end up at the same place, right? Okay. Here's another exponential map. It's called the split quaternions. So these I squared is now -1, but these you get the, the hyperbolic numbers. Okay, you can make cylinders. Every time this exponential map just shows up, everything is exponential growth in a particular sense, huh? Even linear growth. It's a huge cleanup. All right, huh? Economists were the first to come up with the exponential function. Huh? So we did a lot more with it because at least we have these complex, especially these ones, right? Huh? We use all the time in our Fourier transforms, Laplace transforms. Then we have one real one on the real axis, exponent, right? And one imaginary one. So we'll have a complex number. So it's also two-dimensional kind of thing. And these robotics guys, they go nuts with all these quaternions. Also, these guys who make these movies, these Pixar and those people, they use these rotations every time you want to do something 3D. So all it's saying here, we can use this as well in economics. It gets hairy, but it's definitely, sometimes it's just good to know that this is there, right? Rather than attempting to solve it, but, okay. Are you satisfied, Wesley?
Yeah. I was also wondering, because the previous one with the graphs, you had that epsilon, so that is the share, but I think you're getting there.
I think you will have a cylinder, right? Huh?
Yeah, exactly. Yeah.
It's more of a parabolic shape, huh?
Yeah.
Huh? That's if you pair it with a, huh?
Yeah, it's just the rotation and the translation.
Yeah, there's like 3 wheels you can make. You can make a regular circular wheel, right? Huh? And then you can make a hyperbolic wheel, as one of these things. It goes, huh? And you can make a parabolic wheel. It's just like how we walk, right? Chuck, 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 chuck. Huh? It's like a parabolic motion. Huh? Yeah, you're huh? Huh?
Why parabolic? Oh, just what it's called.
That's just what it's called. Now linear is called parabolic, right? Huh? It comes from conic sections, right? So if you have a conic, these are all conic sections. So you have this conic, and then you start, cutting it by a plane. So you do this, huh? And you get the circle. You do this, and you get a hyperbola, and you're right in the middle, going along, and you get a parabola, right? And that's actually a straight line. The metric on it is the Euclidean metric on a parabola, you see, if you figure it out. Because it's right between the circle and the hyperbola. So it's the same as this thing. Huh? You see, this one, here's the hyperbola, here's the circle, what's in between is the straight line. Now the fact that it looks like a parabola doesn't mean that the metric where you measure it isn't just Euclidean, right? Huh? Okay, huh? That's why, huh? So it's, if you take a parabola and roll it, you'll see that what it's doing. You know how you have a parabola? So your lamp, and then you have this bulb here. It will come out with all these straight lines, right? So if you're walking, that's really what's happening. So you're putting your feet, huh? You're going with the the parabolic, but the regular Euclidean metric. So that's why we measure, because we have so many feet or so many paces, like a yard was a pace, right? So that's the Euclidean metric. But if we would use a rolling wheel, I think the Egyptians already had that, you would have a metric that was based on revolutions, right? So many pi, huh? Okay. You could have if you had a hyperbolic wheel, that's one of these cams that are going like this, right? You can also, but this thing goes on for infinity, so you can keep walking with your hyperbolic wheel. It's a little crazy, but those are the three types of wheels you can have. Huh? And the same way, it's the same three types of ways you can grow things economically, right? Acquire things, okay? Either as you're working with the regular Euclidean metric or with a compounding thing, or that's more like a hyperbolic wheel, or with a rolling thing, which is elliptic metric. Okay. This one is familiar because it's but it took us a while because medieval man, he just thought everything was walking. He just walked and he measured distance. So it took them a while to see that the Earth was round because of that, because it makes no sense. Huh? You need a different metric. This thing is turning. Huh? Okay. If you're just walking, how can you come back at the same place after walking a long time? It makes no sense. Huh? And this thing became important with Einstein's theory, right? So the universe, if you look at space-time, it's hyperbolic in the time axis. So now we have all of them. Okay. So the capital theory that you have is a hyperbolic.
Yeah.
All right. That stuff is kind of cool, isn't it? Huh? It's like kind of, this is a cool thing on itself, but what I like is really also, you're so useful for economics, and because economists use the exponential function so often, and there's always this question, why is exponential growth and free motion? Well, because they somehow feel they are in that space, I've been a stock trader, and we were in the same space because we would look at returns and we just multiply them out, right? We'll look at log returns if we wanted to add. That's our reason, huh? And if you thought they added, you wouldn't make any money, right? Because you would underestimate your risk, huh? Because if you add them and you lose 100%, if you make afterwards 100%, you're not going to be back where you started. You're still dead, right? Huh? So if you have an investment, you lose 50%, and then you gain 50%, you're back at 75%. You got the wrong metric, right? For your returns, huh? So it's useful. So just that we do it with ad hoc means, now usually, and you just learn it, but if you're in the trade, you say, oh, no. Huh? And if you don't learn it, you're bankrupt because you take too much risk, now, huh? Yeah, one day you'll lose 90%, and then how much do you have to make, 1,000% or so to come back? Huh? I believe so, huh? Huh? Yeah. It's going to take a long time. Yeah. So I was always a saying, only amateurs lose more than 20% of their holdings, Huh?
I have on Reddit, you have famously Wall Street bets.
Yeah.
So people act like the stock market is a casino, and sometimes you see the losses, like 80%, 90%, and then with a buttload of money, with like the college fund or something like that. So, real nice, yeah.
Yeah, so
Some people also make noise.
they're using the wrong metric for returns. Huh? It should have been on this metric here. They're using the multiplication group. The results multiply, right? Huh? And they're using the Euclidean metric. Huh? They think they're walking, but they're not. They're expanding. Huh? And contracting, really. Huh? Yeah.
No, they find out after that happened to them.
Yeah, either they find out or they die never to come back again. So you either way, you get rid of them. Huh? Uh-huh. But this is a real economic problem, where you see that if you're in the wrong space, you just things are not gonna work out for you. Huh? So, of course, this is all kinematics, but once we start putting dynamics on there, we're gonna assume that we have some structure on this space that allows us to talk about free motion and that kind of stuff, Huh? Okay? So, huh? So we can talk about price stability, which is conservation of momentum. You have to go at a constant rate. Price stability only gets if you have constant demand for something. But what is constant demand? At what, huh? Demand for returns is obviously goes different than demand for, I don't know, huh? Okay, huh? All right. And this is just fun stuff, okay? Because you're still at a university, guys. Huh? Huh? You still have to appreciate the theory for just being a pretty theory. So that's really this Lie groups that kind of puts everything together. So I'm going to give you one more example, and then we're done. Huh? So that's a business, all right? So I'm now not going to look at these rotations. This is just a yield or something, right? So I'm going to take a business, and the capital is just your initial capital. You put it in, right? Huh? Okay. And let's first look at it as a body. So there's this body. It's some kind of body. In this case, it's a rigid body, and it's got these 3 masses here, 4 masses, right? Huh? Okay. I guess this one is not even rigid. Oh yeah, it is. So, but whatever. So then I have these ones. So what's going on here, right? So suppose I had. I'll just make it, first let me make it easier. So we had something like this, where we were going up along a line, that's our yield. But now suppose we have 2 things, right? This is our asset, which is land, but suppose we borrowed some money, right? So we have something else that we would call a liability. I'll put that right here, okay? And suppose the liability is just as big as our asset, so we're measuring them in money, both of them, right? For the moment, we're not assuming this price is constant, okay? Then here I get yield, and here I have to pay something, right? Okay? So this is another dimension, maybe money, but I don't want to look at it that way. I'm going to think of myself as a medieval farmer. I have no land, so I have to borrow it from my overlord, my feudal lord, right? And I make this crop, and I have to hand him over the same amount that I make. So I don't have anything for myself. All right? Huh? Let's assume you can do that. Okay? Huh? So then you really have this loan, and you have this asset that you can use, right? And this one is going down, and this one is going up. So you get what we would call a couple, right? Huh? Right? So this thing is just a seesaw going like that, huh? Shearing out. Okay? We don't have a couple because I don't have any forces, okay? And if you then look at the total velocity, this is the center of mass. Will that change? No, it won't, because it goes up with v and it goes down with minus v, and the sum is just going to be 0. So the thing is just shearing like this, okay? Okay? So somebody with an asset and a liability, you can think of them as like a seesaw, right? With the fulcrum right here. And it's not turning, I agree, but it's kind of, think of it as a very large circle, right? Huh? This parabolic circle, okay? All right? So that's already interesting. So I can add more things, right? Huh? And then you see that this thing is in balance as soon as your assets and your liabilities yield the same amount, okay? Huh? And you know that the balancing point is where the fulcrum is. That's, that's where it says your assets equals your liabilities in this metric, all right, that you put in there. Now suppose these are not the same, right? This is smaller and this one is bigger, like I had over here, right? Huh? Then what's going to happen, this thing will also start turning, right? But the center of mass will start moving up because it's going to be the sum of a large positive thing and a smaller negative thing, so you'll get a net positive, right? So if I look at this as a business with its assets and liabilities, what's going to happen is it will start moving upwards, okay? Now, if I look at this as the capital of the business and this as the earnings, you'll see it's generating earnings because what it's receiving is bigger than what it has to let go, all right? Huh? So you'll see the center of mass motion is equal to the net earnings, okay, of the business. And the motion of the assets, that's, the one, and that's the other one, okay, the balancing. You see that? Huh? So that's interesting, okay? Now this is also a group. So I can recognize SO2, right? Huh? Well, this funny version of SO2, right? Huh? Okay. But there's another group, namely the translation group, that's saying you can move this way. Huh? I can also throw some capital in. I did make another capital contribution. I go this way, right? Huh? So this is a group that consists out of translations, 2 translations, okay, and 1 rotation, okay? All right? This group has also a name. It's the Euclidean group. Because Euclidean motions are translations and rotations. So our space is invariant. I can take this thing, put it somewhere else, or I can rotate it. It's the same object. If I stretch it, it becomes a different object. Okay? That's why it's called the Euclidean group. And its name is SET, Special Euclidean Group. Special because these rotations, are special. Now, we don't have flips. Okay? Huh? We don't have flips. All right, orthogonal group means that you can or rotate or put it in a mirror, and I'm leaving out the mirroring. Okay, don't worry about it. It's not important, especially not here. Okay. All right. Huh? Now this is a complicated group because it consists out of R2, which is the translation group that we had before, but then in 2 space. Okay, and this circle group, but they are not independent of each other. You know that if you do a rotation and then a translation, it's different than first a translation and then a rotation. You know that, right? Because if this weren't the case, that's the car example. In a car, you can drive and steer, right? So you're translating and you're rotating, right? Huh? And you wouldn't want, it's just not true that when you are in a parking spot and you want to go somewhere, you can change the order and first do all the driving and then the steering, okay? So we all know this, right? There's an interaction, right? Huh? So if I rotate and then translate, or I translate and then rotate, I get something else, okay? Huh? And the way they indicate this is by this symbol, right? That's a semi-direct product, okay? Whatever. This tells you how that interaction works, all right? Huh? But the group is still this. You can just describe it as translation, semi-direct product with rotation, all right? Huh? Okay? So it's a much bigger one. How many parameters does this one have? Huh? 3, yeah? 2 here. So you can either increase your capital or you can get some earnings out of the company, right? Huh? All right? Huh? Or you can run your business, which is just a shearing action, right? Okay? That's how you run your business. If you make no earnings, you're just sitting there, you know, well, actually you're just shearing and nothing is happening, right? Okay? Without making a profit, that is. Now, the way we deal with this semi-direct product in engineering practice is as follows. We take 2 frames. We take one thing that we call the spatial frame or some inertial frame or something, or sometimes they call the lab frame. You just attach it here. And then you take another frame and you attach it to the rigid body at the center of mass, right? You know this. Now that thing is not translating this frame. That thing is just rotating, okay? And then you look at the rotations from this frame. And then later on you add, you know, huh? And then you have to translate between these 2 frames. And that's a tricky business because it's much easier to deal with the center of mass frame. And then you try to separate it, but it's a mess, okay? But that's how we deal with it in practice, okay? That's what this thing is saying, really, okay? Now, what does that mean economically? What is this frame and this frame? Well, this is the frame of the body itself. So that's if this is a business, that's the frame that somebody who's running the business, who's inside the business, is using, of course. He knows how fast he's running his business, how much he's paying here and how much he's paying there. But he doesn't remember how much he's paid out to the investor, right? That's just the capital contribution. He's the CEO. He doesn't bother himself with that. That's the investor. So the investor is here. The investor gets the paid out earnings. That's this. This is what he got, right? This distance. Huh? Okay. The investor had to make the capital contribution. He's here. Okay. All right. Huh? And in his frame, the center of mass is moving because that's the stuff he gets. He doesn't really care about the internal workings of the business. That's all the rotating. He just wants to know, what is the center of mass doing, right? Huh? Okay? That's my earnings, and that's how much I have invested in there. This is how much he has got invested. This is the earnings he's pulling out. Okay? And how they balance their liabilities and their assets. If I buy the shares in Microsoft, I would have to do my research, but in the end, I don't care. All right? Huh? You see? So the investor frame is really what we would call the spatial frame, right? And what we call the body frame is what I would call the management's frame. All right? Huh? Okay? And for management, the problem is simpler because once they've paid out their earnings and everything, they don't worry about it, and then they just start analyzing how to run the business rather than how to make all the payouts and what the, okay? But the investor, he worries about this part, and the business owner, he worries about that part. The total problem is what in the special Euclidean group in 2 dimensions. It's a big problem. It's a complicated thing. Our friends in robotics, they deal with this all the time. They have a more complicated one. They deal with SE3, right? Robots move in 3 dimensions. You know, you got to know where it is, and you got to see how it turns. All right? Okay. But there's whole books written about that. There's a really good book, I think, by Sastry and 2 others, that gives all the Lie group theory of this. And how you can see, I didn't give you the exponential map. It turns out that it's not so easy. It's a matrix, so you can write this as the changes in terms of a matrix. You know, you'll have some rotation matrix, and you have a velocity, but a bunch of zeros, and here a 1, right? You probably know this, right? And then you multiply that by t, and you take the exponent of that, and then you get your position. So again, you'll use the matrix exponential. So you'll write the velocity, the quantity demanded, right? Which is now demand for capital, demand for earnings, right? Quantity, and the demand for business cycles, right? They're running, okay? And you put those in there, and then you integrate it out, and then you'll find the stocks. There will be another matrix. How are these matrices called? I think so. Some kind of homogeneous matrix because they got the one here. It's yeah. They may have a name for it. No, this is just the Lie algebra of SE3. Right? Really, that's how I know it. But they may have special names in it over at aeronautics. But this is how you would look at an airplane, right?
It's more for multi-body.
Yeah, multi-body stuff. Yeah.
Because then you can somehow compose the. You also did something.
Yeah.
Yeah, but I have to grab my old notes because we are edited in Python. So you had libraries that did those incredibly complex rotations for because if you have to do it for a frisbee and you look at that corner, you can do it by the hand, but you're busy for 4 years or something. Yeah. Matrix got huge.
Matrix are huge.
So I do remember it.
But Python will use the exponential map, the matrix exponential.
Yeah, there was a library developed by a professor here, over here.
Yeah.
Or partially developed, and he had a Python library where he could describe very complex multi-body rotations with transfer matrices. It was really interesting, but also difficult, but interesting.
You can use them for businesses, right?
Apparently, yeah.
Yeah, a business is a rigid body or non-rigid body, I don't care. You know, multiple goods, And then you have the two frames. You have the body frame, that's where the business CEO works in, and the spatial frame, and then that's how you do, Yeah. So again, you're just using the exponential map. Everything is exponential growth in some form or another, even linear growth. And that's where I want to end this. I mean, you can go nuts on this stuff, okay? But what I do want to have here is that this theory, look, all these are legitimate examples, more than legitimate examples of economic problems, okay? Really fundamental problems, you know? Just to warn you that not everything is a commodity. You just do F is M times A, all right? And they're all, if you treat them separately, it just becomes a big mess of specialized tools and this. And once you take that step back and say, all right, there's really only one thing is going on here. What's the metric? What's the symmetry group, you know? What can we do? How do we describe our activity, right? Then you have these tools that just kind of clean it all up and make it all the same, you know? And you can define forms of capital, which are the conserved quantities here, right? That's the radius, whatever it is. You know, you can define a return, that's the angle, whatever it is for the specific application, you know. And you can do the compounding using an exponential function, you know, which is just the way you move forward at constant speed kinematically, all right? So that is the cleaning up you do. Otherwise, you get your pretty head all bothered about this, and you'll keep wondering what the connection is between it all. All right. And as engineers, we're in great shape because you can just tell me how you solve this SE2 problem. You know, everybody kind of recognizes it. They just never realized it was all part of the same problem, and that it has an economic analog. You know. I would say economists are in bad shape because they have no experience with this kind of tools, right? You know, some do, but then only at the mathematical level, not at the practical level of what libraries to use and how to do it. Okay? So I want to, unless there are further questions, I want to end here, and then next week we'll start doing the dynamics. That's when it gets, the kinetics. That's when it starts really getting fun. And then we'll use this symmetry again to look at symmetries of our Lagrangians, you know, the cost, and those kind of things that would allow us to solve all these problems like why a business is at rest or a mortgage would have to go like this if you're not applying forces or incentives, okay? All right, so that's it.